Thank you all for coming this evening. Some of you came from quite a long distance, so thank you again for coming. I wanted to take the opportunity this evening to tell you about a crazy idea that I heard about 20 years ago. And hopefully by the end of the evening, or at least the end of this lecture anyway, I'll be able to persuade you that it wasn't such a crazy idea after all. So we'll wait a little bit of time for crazy. Let's start with the LHC. I thought I'd start talking about the LHC because, not because I work on it, there's lots of people in the department who do work on the LHC, but because the LHC is the one physics experiment everybody's heard about, right? It's on the evening news, it seems almost nightly from time to time. And the LHC, probably you all know this already as well, stands for Large Hadron Collider. You probably know this for your pub quizzes, right? What the Large Hadron Collider is, it's the world's largest accelerator, and here's a picture of it, or to be more accurate, it's a picture of the countryside around Geneva. So this is the countryside on the French-Swiss border, and you can just about see, actually maybe if I turn the lights down a little bit here, I'm going to see this a little bit more clearly. Cut away underneath this lovely countryside is a huge 27-kilometer long tunnel, and there you see a little bit of the tunnel. And if we were to actually look under the ground, underneath this big red line, which is where the LHC is, this is what you would see. And so what you find at CERN is that there's a series of interconnecting rings of ever-increasing size, and all these are part of the accelerator. And so protons from the CERN complex begin their life somewhere down here at the bottom, and what you'll see is that they'll go around these rings, and as they go around these rings, ever-increasing size, they're increasing in energy as well. And so here's one proton bunch which is going, and it's going to be followed by another proton bunch. You can just about see them. It's a little bit dark, and I apologize for that. Eventually, they get tired of following each other. One gets switched one way, one gets switched the other way, and they go into this big ring, which is the Large Hadron Collider itself. And after getting to a prescribed energy, they're allowed to collide. And when they collide, now they've gained so much energy. We use the physics equation that everybody knows, E equals mc squared. Some of that, well, hopefully as much of that energy as possible is turned into mass. And it's turned into not just any old mass, hopefully it's turned into mass which is a whole different types of mass than you would find in everyday existence, whole new different types of mass being produced, whole new types of different types of matter being produced. And so what does the LHC actually, oops, I went the wrong way. What does the LHC actually work on? Or what's it there to do? Well, when you produce this mass, so here's some of the questions the LHC actually hopes to solve. When you produce this mass, one of the things you normally notice is that mass gets produced with equal amounts of matter and something called antimatter. Antimatter is material that when it meets matter, it annihilates with itself. And so, for example, electron and positron, you might have heard of, are antimatter particles of each other. They're here being produced in the first record of antimatter being produced. As far as we know, whenever we do a particle physics experiment, matter and antimatter are produced in almost exactly equal quantities, which is really quite surprising because if we look around our universe, what we actually see is that there's a huge preponderance of matter over antimatter, right? So where did all this antimatter go? And that's one of the questions the LHC hopes to answer. Another thing the LHC hopes to find is that they hope to create particles which have never been created before, never observed before, which are even heavier than our normal standard particles, but somehow related to those particles, but very weakly interacting. And if we could find those particles, then maybe we'd be able to solve one of the outstanding problems in cosmology is the fact that most galaxies, most of the universe seems to have more mass than we can actually account for, that we can count and see in the night sky. So for example, from the rate at which galaxies spin, we know that all of the galaxies have something called dark matter in them. And it could be that these weakly interacting particles could somehow explain dark matter in the universe. And the third thing, of course, I wanted to highlight today, but the one pretty much everybody's heard of, right, and gets a lot of press as well, is the search for the Higgs boson. The Higgs boson is, of course, the particle that is supposed to explain the mass of all other particles, interacts with all massive particles. And it's the particle, I like to say, gives balance to the standard model of particle physics, which is the overriding model which has so far been used in particle physics to describe the whole zoo of particles that are created in particle physics experiments. And people from this department are pretty much closing in. They think they're closing in on finding the Higgs boson, right? You might have heard announcements before Christmas that they think there are the first elusive signatures of this elusive particle being produced. And there might be a lot more as well. Almost every generation of particle accelerators that's so far being produced has found almost new things that we never actually thought we would find initially. So you could actually say that particle accelerators are somehow the engines of physics discovery. For over 100 years, they've been finding new particles and new physics as we go to greater and greater sizes. Let me tell you a little bit about the energy of the LHC. So as of a couple of months ago, they just upgraded the LHC to 4 tera electron volts. That's 4 million electron volts. And for the non-physicists in the audience, an electron volt is a physics unit that is the energy you gain when, say, you had a 1-volt battery and you took an electron going from one end of a battery to the other end of the 1-volt battery. 1 electron volt is the energy you would gain in that process. And so this is 4 million of those electron volts. And just to put that in proportion, right, so eventually the LHC, at the moment it's going at 4 tera electron volts. It'll run for a year at 4 tera electron volts. And after this year's shutdown, they'll shut down for about a year, and then they'll go to its final design goal of 7 tera electron volts. And these kind of energies, as I said, just to put this on a human perspective, it's the energy that the kinetic energy that a mosquito has in flight. Now, that might not seem a lot, right? But you remember that this is just one particle which has all of the energy that those millions and millions of particles in the mosquito would have otherwise had. Or if you're still not impressed by that, if you add up all of the energy in all of the protons in a bunch inside the LHC, then you find that the energy is something approaching the kinetic energy of a jumbo jet, or as the French like to say, of a TGV train. Hopefully you're impressed by that, right? One tip I have for you this evening, don't ever walk in front of an LHC beam, because they'll do some damage. Okay, to get to 4 million volts, you think, okay, as I explained it, all you need is a 4 million volt battery, right? And if I have a 4 million volt battery, I can just put electron from one end of the 4 million volt battery and take it to the other end of the 4 million volt battery. I've said that too many times now. Actually, of course, 4 million volt batteries don't exist, not even in Tesco's. So what you have to do, and that's the reason why LHC is so big, right? You have to accelerate in little sections, and each of these sections tends to be around a mere 10 million volts per meter instead. And so, but you know, this is quite a way off. This is just millions, and this is millions, and so you find you need to accelerate to get to these kind of energies. You need to accelerate on the order of millions of meters. And that's why LHC is a circular accelerator, right? It's so that the same particle bunch can go around that circle and come back and get reaccelerated and go back and get reaccelerated. And they have to do this for a very long time. Typically, to get the protons in the LHC up to full energy, it takes them about 20 minutes. And while they're doing this, if you're ever in the LHC control room, you'll see a big board up in the control in one corner of the control room. It tells you how much energy the LHC is using, and typically the numbers are in the 100 megawatt, 200 megawatt kind of range, which again, for the non-scientists in the room, that's probably more than the energy being used by the city of Geneva next door at any given time. So it's an amazing thing, the LHC, and really is an amazing thing, and we really hope, I think everybody in the physics community really hopes that they're going to find some of these questions. I mean, I told you that it's going to explain how the universe came to be. Oops, sorry, I'm going to press the wrong button. How the universe came to be, how it is in the structure that it is at the moment. So these are really deep questions. Hopefully, all of you can see that those are questions that would be really nice to answer. Sorry, I'm going through my talk again. That's okay. Because I pressed the wrong button. However, there is a problem with the LHC that you don't hear said on the evening news very often. And the problem with the LHC is this. When you collide protons together, two protons together, protons are actually not fundamental particles at all. They're not the very basic building blocks of particles. Protons are actually made up of something even more fundamental. They're made of things called quarks. And quarks have associated within the proton, there's a whole zoo of associated particles called gluons and things like that. Things that kind of stick the quarks together into that proton. And so when you're firing two protons against each other, what you're doing is not actually firing one particle against, it's not a billiard ball collision against another billiard ball where you can stop them both and turn all that energy to mass, which is what I said we wanted to do. In fact, what it's more like is throwing two garbage bags against each other, and all these garbage bags, out of these garbage bags, you hope one bit just had enough energy that would create the right particle that you wanted to generate. And this makes a logistic nightmare. I mean, the LHC is an amazing thing, not just from the accelerator point of view, but from the actual diagnostic and the computation around it that's required so that when you collide these two protons together, you generate a huge jets of particles everywhere. And to be able to sift through all of those and actually find the event that you want out of the many, many jets of different things being produced is a really challenging assignment. And that's why it's actually proving to be very, very difficult to find clear signatures of the particles that they want to find. Actually, what physicists would really want is they would actually prefer something, their ideal accelerator would be something that's much cleaner, would be something that is really a point-like particle colliding with another point-like particle. For example, electrons and positrons are, as far as we know, almost perfectly round. People have heard that before somewhere as well, right? And in those collisions, there's something even nicer. Electrons and positrons, as I said before, they're antimatter particles of each other, so in theory they can annihilate, and all you're left is with pure energy to create whatever you want to. And you can do a lot more control things with electrons and positrons as well. So why is LHC not an electron-positron collider? Well, actually, it used to be an electron-positron collider. It used to be, actually, I forget when it stopped being an electron-positron collider, but it was an electron-positron collider called LEP, the Large Electron-Positron Collider. Not very original names. Well, actually, I tell you the reason that it's no longer electron-positron collider, and this diagram will need a little bit of elementary physics knowledge. I'm going to show you the electric fields of an electron. Some of you will know that an electric field of an electron is a radial field it'll point out every direction. And actually, electric fields travel at the speed of light. They travel outwards at the speed of light. And so this is what the field, oops, sorry, I went too far again. This is what the electric field of electron looks like. And if you put another charged particle next to it, the electric field lines tell you in which direction forces would be felt. Okay, now, if we make the electron travel around in a circle, as if we were in the LHC ring, being accelerated at very high energy, then this is what happens to the electric field lines. And so the obvious thing, I hope you should be able to see that, is that the field lines aren't straight anymore. In fact, these little kinky things are bits of electric field that point in the other direction. They point transversely to the direction the field line is moving in. And so these things are a representation of electromagnetic waves, right? Ordinary electromagnetic waves, X-rays, light. What you're seeing here is something that's called synchrotron radiation. So this electron traveling around in a circle is just radiating a lot of its radiation, a lot of its energy away. And if you left it for enough time, if you put electrons in the LHC ring and got them up to TeV energies, well, they would almost immediately radiate all of their energy and throw it into the walls. And so the Large Electron-Positron Collider, when it was going, only ever got up to about 100 giga-electron volt, which annoyingly is just out of range of the Higgs boson. They stopped almost just below where people think the Higgs boson would be created now. And so, but there still is a lot of mileage, right? There's still a lot of mileage. You could do a lot better experiments if you did have an electron-positron collider. And so obviously, the way to stop this radiation happening is, if you're keeping up to date so far, is to not make them go in circles, right? What you want is your accelerator to be a straight line. And so if you accelerate electrons and positrons in a straight line, they won't radiate. There's a problem is that you can't keep on recirculating them and use them again. The other problem is, of course, you can't keep on accelerating around the ring, and now your accelerator has to be very, very long, right? And so people talk about this accelerator, the ILC, which is the next generation, the collider that people hope will, once that they've discovered the Higgs boson, for example, they can narrow into the energy range where they find the Higgs and really be able to do some sophisticated physics with it to really determine the properties of the Higgs with great detail. And this collider is, the next future collider is called International Linear Collider. And, well, there's problems with the ILC as well, and I've said it already, right? It must be huge. It has to be a minimum of 30 kilometers, and it has to be a straight line, so it's no accelerator that's been built already. And already, many governments are already balking at the idea of spending money on this kind of accelerator. Britain, for example, pulled out of ILC development a few years back. Okay, I know there's a few of you smart ones in the front, especially, I know, who are thinking, okay, your accelerator is too big, why don't you just accelerate them faster? Why don't I just make my accelerator have even greater electric field? And so just turn up the knob on my accelerator, right? So turn up the electric field, that's all I need to do, right? Keep on making my electric field larger and larger. And so here's an example of my little accelerator out here, a little demonstration accelerator. And I'm just turning up the voltage on it at the moment. It's got 10 kilovolts. Nobody stand up, please. Everybody turn off your phones as well. You might want to do that too. We're about 15 kilovolts now. 20 kilovolts. You might, some at the front might hear a little hissing noise. That's what happens when you turn up your electric field too much. You create something, as well as messing up the screen every once in a while. You create something that's called a plasma. I'm going to turn this down for the sake of the AV to work for the rest of the lecture. And it's for this reason, as far as I ever understood it, accelerator physicists hate plasmas. And by extension, I think accelerator physicists generally hate plasma physicists as well, which is a bit of a problem for me because I'm a plasma physicist. So, okay, there you go. That was our problem. If you try and turn up the electric field too much, you produce a plasma. Okay, here's the crazy idea of part one. Crazy idea of part one is the reason we can't turn up our electric field anymore is because we're destroying our material, the materials that create the accelerator, right? We're making it break down. So why don't we start with a material that's already broken down? Why don't we use the plasma as our accelerator? Seems like an idea. So let's start with that. So let me explain to you what a plasma is before. Again, the non-physicists in the audience will probably think, I know what a plasma is. It's something to do with blood. Right? And well, you're not very far from the truth because the person who termed the phrase plasma to describe ionized states of matter actually did it because he imagined that they looked a little bit like blood plasma, believe it or not. And so he imagined that the ions inside, so this is your initial atom. You take electrons from an ion. Again, a little bit of physics. I apologize for people in the front. You take an electron from an ion, and you have these things which look like white blood cells, and you have the electrons which look like little red blood cells. I don't know what he was taking at the time when he imagined all of this, but anyway. There's an interesting property of plasmas, right, is if I move the electrons a little bit out to one side, now I generate an electric field as I've separated my ions and electrons a little bit, and if I let them go, the electrons will sort of oscillate around this medium position. And that's called a plasma wave. And that plasma wave can, in theory, have huge electric fields. As I said, there's nothing going to break down this plasma any more than it's already broken down, right? It's a destroyed kind of material, so we don't have to worry about electric breakdown voltages anymore. Okay, some of you at the front, again, might be thinking, okay, right, so it's a wave. It's an electric field that's in a wave. How does a wave accelerate anything? Because I've seen ducks on a pond, right? And the ducks don't seem to go anywhere. They sort of, you see ripples go past them, and the ripples go past them, and the duck sort of ends up sitting basically where it started out, right? Yeah? I'll show you an example of a wave that's accelerating somebody. I was going to try and pass her off as me, but since my family is here, I don't think I can get away with that one. This is a wave. It's a huge wave, obviously, and the surfer is getting energy from it. He's moving along with the wave. And if there are surfers in the audience, okay, didn't expect that. If there are surfers in the audience, you know the trick to being able to start surfing, right? The trick you have to do is you start on your belly, usually start paddling along with the wave. And what you try and do is you try and gain some significant fraction of the wave speed as you move along. And so if you do that, so here's the little duck, and we're going to start him with a little bit of motion in the direction of the wave now. And as he goes, he's starting to stay on this slope of the wave. And so that slope of the wave is helping him push forward, right? And you saw that duck surfing. And so if we make a plasma wave and we let electrons surf along that plasma wave, that's the way it's going to gain energy from that plasma wave. Okay, that's crazy part one. Here's crazy part two, is how are we going to make this plasma wave? And actually, it's not as trivial as it seems, right? So to be able to make those separations of electrons and ions, you need pretty huge forces, right? Those electric fields are enormous, so you need pretty huge forces to be able to do that separation. And so this was the crazy idea. It's the title of the paper is it's more than 30 years old now. It's Laser Electron Accelerator. And the idea was that you would use light to make that plasma wave and to push all those electrons forward. Now, I've got an example of light here in my hand. This is a laser, actually, even better. It's lasers, as you know, single frequency and very directed light, so that's even better. And this is about the same brightness as sunlight. It's about 1 kilowatt per meter squared, something like that, right? And I shine it in my hand, and oh, sorry, I should stand still when I do this. My hand is not going anywhere. And, okay, you're saying that's a pretty stupid example because my hand is quite heavy in the relation of all these things. But even if I shone this laser light at an electron, the electron would really not go anywhere. And so what these two physicists, Tajima and Dawson's one of the great plasma physicists, by the way, they proposed that rather than at 10 to the 3 watts per meter squared, if you took a laser which was 10 to the 18 watts per centimeter squared, which makes it 10 to the 22 watts per meter squared, which is 10 to the 19 difference, that's 10 million times brighter than this laser. That's a big number, yeah? Then if you had that brightness of laser, then the pressure that laser would exert on the plasma is enough to actually push some of the plasma out of the way and create this plasma wave. Now, the particularly crazy thing about this thing was at the time, there were no lasers anywhere close to 10 to the 18 watts per centimeter squared. This was 1979. But anyway, we'll reserve that judgment on theorists for a little bit later. Let me show you if you did have this super intense laser pulse going through a plasma, what would happen to the plasma. So here we're going to actually, thought experiment, we're going to move along with this is a laser pulse, and we're going to move along at the speed of light, which you can't do in London anyway. All the people who've come here this evening tell you travel much slower than that. And so we're going to come up to a plasma boundary, and the plasma is going to stream through this laser pulse. And you'll see what happens to it. So here's the plasma coming, and it gets pushed out by this incredible pressure of the laser pulse, and it forms kind of a sheath around the edges of the laser pulse. And then when the laser pulse is gone, then the force due to the laser pulse has gone away, and so the electrons come back, and they oscillate backwards and forwards and backwards and forwards. And so behind this laser pulse, you'll get a wave, exactly a wave. You'll get a train of waves, which look a little bit like the circular, so we sometimes call them a bubble accelerator, mainly because we don't have that much imagination. Anything circular in physics gets called bubble something or other. It doesn't have that much more in common with a bubble, except for the fact that it has a high density outer, and in the middle it's kind of relatively evacuated. But anyway, associated with this are exactly the electric fields that we wanted to generate.
And so if you're an electron, one of these electrons, you're always feeling a force towards the center of this bubble. And so let's for example, find that we had an electron that somehow managed to get itself into that bubble. We won't exactly go into the details of how it got there. But let's imagine that it starts off somewhere around here. Remember, it's going to feel a force always to the center. It's going to feel a force making it want to go this way. Eventually, when it turns around, it's going to want to have a force making it go in that direction. And so as it sort of slips back, it's gaining energy. And if the bubble is big enough, it'll turn around and start moving in the direction of the bubble. And because this bubble was traveling almost at the speed of light, this particle now is also, initially it was traveling backwards almost at the speed of light. Now it's traveling forward almost at the speed of light, which means it's traveling very, very fast. It's a very, very energetic particle. And that's exactly what we wanted, right? We wanted to use these electric fields to be able to turn around the electron, make it move at the speed of light. Okay, now going back to the crazy intensities. So I was very lucky, and luck always plays a big part in science. So I was very lucky in that when I started my PhD, actually the lasers of the kind of intensities that Tajima and Dawson had mentioned in 1979 were actually becoming a reality. And they were becoming a reality because of a process called choke pulse amplification. Again, I won't go into the details, but basically what you do is you get a laser pulse with, you play some clever tricks, you get a laser pulse with a lot of energy, and you just compress it up into a really, really short time span. So here you take a laser with a reasonable amount of energy, and you really compress it down into a very short time span. And now it has that incredible intensities that we talked about, those 10 to the 18 watts per centimeter squared, even greater than that. And so, so the first few months that I started my PhD, my supervisor, Bucker, sent me to the Rutherford Appleton labs. And I spent 3 months there helping to upgrade a laser called Vulcan laser to this kind of intensity. And we actually tried to do an experiment to look into what this laser would do when it went into a plasma. Here's some of my colleagues from that experiment. Actually, we contacted, Bucker contacted, my supervisor contacted some of these the theorists who'd been predicting what these laser pulses would do. And actually, even though 1 picosecond, I should have said what 1 picosecond is a million millionth. I know there's a lot of millions. I almost sound like a banker, as everybody says. But 1 million millionth of a second may seem like a very small time to you and I, but actually it's a little bit long still for this plasma accelerator for the wake field generation. And so we told this theorist that we had this high intensity laser, but at a picosecond long duration. And they told us, don't even bother doing the experiment. Nothing interesting will happen. All you'll do is blow out all of the electrons and all of the plasma all the way out of the interaction volume, and nothing, not even worth doing the experiment. That's what they told us. Anyway, we went and did the experiment, right? And what we found is here, this is a little bit of a complicated slide. I apologize for this, but this is a spectrum of our laser after it's been through the plasma. And as I've said already, one of the things about a laser is that the purest color, right? If you normally look at the spectrum of a laser, it only ever has one color component to it. And this one has got multiple color components to it after it's been through the plasma. And the reason that's happened is because as our laser has been passing through the plasma, it's sort of broken itself up into beamlets. It's broken itself into those tiny little pulselets exactly as we wanted to generate a plasma wake field. And this is almost a miracle in itself, right? This is an example of a plasma actually helping you out to do what you wanted to do. The people here, I mean, Steve talked about people who work on fusion in our group, know that plasmas never do what you normally want them to do. So that's kind of an amazing thing in itself. And in fact, because all these beamlets are really high intensity pulses, what happens is there's a plasma wave growing at the same time, just as we wanted to grow, and the plasma wave keeps on growing. Actually, in fact, we're almost too successful at growing a plasma wave, because the plasma wave grows and eventually it breaks, just like those big sea waves as they come onto shore, get bigger and bigger in amplitude and break, and then send a lot of the water spray forward up the beach, right? And all the rubbish that you've thrown into the sea before also gets thrown back onto the beach as well at the same time. So actually, what happened is that our plasma wave grew so big that it broke, but it accelerated some of the particles up the beach, or our target area at that time.
And so we got electrons up to 50 megaelectron volts. Again, if anybody knows a little bit relativity, you know when you have an energy greater than your rest mass, you start to feel heavier. So these electrons are 100 times heavier than they initially started out with. Relativistic effects coming into play. And this was a big deal, right? This was a big deal because eventually we went up to about 100 megavolts. And so this was 100 megavolts, but in a plasma that was about a size a millimeter. This was a little, tiny little plasma that we did this in. And so 100 megavolts in a meter is 100 gigavolts in a, sorry, did I get that right? 100 megavolts in a millimeter is 100 gigavolts in a meter. And as I've told you, 100 gigavolts is about the energy range of a Higgs boson. So imagine that you have two of these, meter long, you could generate Higgs bosons in your living room, right? That's the implication of this. You're really generating huge electric fields, thousands of times greater than we said we could do with our conventional electrodes or whatever. Anyway, as I said, these things were published in Nature, and when that happens when you're a student, that's a big incentive to go on and do a little bit more of this research. Yeah, people who've been up to my office have seen these computers there already. That's why they're laughing. And the reason they're still in my office is because of that. I don't really have the heart to ever throw them away. And also, probably around that time, people who knew me in the group here probably didn't even know that I was an experimentalist. They probably thought I was a computational physicist, mainly because I spend most of my time messing around with computers. And you know, to be fair to me, all of our experiments were done at the Rutherford lab, so they would never have seen me do an experiment. But anyway, I did manage to get a hold of these. This is the days Apple used to make computers, not phones, right? I did get a hold of these G4, dual processor G4 computers and hook them together. And that was one of the things that I managed to do. And I've heard other people, in fact, I've heard a previous head of department say that he was instrumental in making the first computer cluster in the Blackett laboratory. I reckon this was the first computer cluster in the Blackett laboratory. I mean, it was only a small thing. It was only four computers, and it was only 8 nodes. But it allowed me to do simulations of these kind of complex interactions at up to 8 times greater speed. So it allowed me to start simulating some of these experiments that we were doing. And so around the same time, I've told you about the spectrum that was not ideal, right? That we'd seen accelerated electrons, but we'd seen lots of electrons with lots of different energies, and that's not what you really want from an accelerator. The ideal accelerator would have electrons all being accelerated to one energy. And so there was a theorist who was going around saying that if you had a laser like Vulcan and you took all of that energy of Vulcan and compressed it into a kind of short pulse, a really short pulse, that you would be able to generate, just the pressure of the laser would be so great that it would stop the plasma wave from decaying, from destroying itself. And you could generate these small energy spread beams of electrons, which would be ideal for some applications. I then sort of went to him and asked him, well, would you be able to do the same experiments with the lasers that were available at that time, there were some lasers with really short, the kind of short pulse lengths that you needed, but not the energies you needed, something like 100 times less the energies, or 10 times less the energies that he was requiring in his simulations. And of course, like any theorist, he went and told me, nah, absolutely not. Don't even bother doing the experiment. So as I said, I was doing some of my own simulations. Oh, you never believe a theorist, right? So here is a simulation of a laser pulse going through a plasma, a little bit like that cartoon I showed before with a circular shape, except there's something a little bit strange happening at the back, right? Here, there seems like there's no electric field at all. And so it's almost a bubble shape, but with a bit of the bubble missing at the back. Actually, you can see what's happening if you look at the energy of electrons. This is, again, the energy of electrons going up as a function of their distance in that bubble. And what you see is some of the electrons are actually breaking away from that motion of the bubble and being accelerated. And they're all kind of being accelerated almost at the same rate. So they're all kind of being, rather than being a big spread of energies, it's almost kind of what we wanted, right? Not exactly
this broad energy spectrum anymore, but a reduced energy spread spectrum. And in particular, I think you can see it very clearly here. If I look at magnetic fields, right, if you see a current of electrons, you know that they generate magnetic fields. And so here again, you see the bubble structure, and here very clearly you see where there's a current of electrons produced that are being accelerated. And actually, I propose to use looking at these magnetic fields as a diagnostic of these interactions after I'd seen these simulations. So being able to do these simulations myself was a really big incentive to try and do this experiment, right? The only problem was we didn't have the laser exactly. Though there were lasers with that kind of spec around the world, we didn't have that laser available to us. And so we did something a little bit naughty, probably we weren't allowed to do at the time, but we spent some of our own grant money to try and get one of the lasers at the Rutherford lab, which is the Astra laser, upgraded so that it could do this experiment, so do exactly this experiment. Yeah, there's a few people who you might recognize in this picture. I have to say, I'm very picture to be proud of, because out of the 3 students who are working on this experiment, all 3 are lecturers now. A couple of them are here. One made the feeble excuse of being on his honeymoon to not be here. But, so I'll never forgive him, anyway. So halfway, so we were getting this Astra laser at Rutherford upgraded to be able to do this experiment. And halfway through this upgrade procedure, we had an experiment. It was towards the end of 2003. And, probably, I mean, obviously there are some days in your life that you always remember. I remember very well the day I first saw my wife, Mubaraka, who's, yeah. She's here. Sorry, Mubaraka, I'm going to compare a day in the lab to you as she always accuses me of doing, but anyway. But so an equally memorable day, no, not an equally memorable day, sorry. The most memorable day of my scientific life was the last day of this experiment, just me and Chris around at that time. And, I was really pushing, even though we hadn't quite got up to the spec of required for this experiment, so we really have to try and do this experiment. And so, Chris was taking the shots. I was running up and down the job, which is usually reserved for students, which is developing, we use a rewritable fill, and you'll see it come up here, which you scan out. It's called image plate, and it gives you, it shows where radiation passes through. So here, we're looking after our electron beam that we've generated has passed through a magnet, and so they're resolved by energy. And this is the kind of broad energy spectrum that you saw in our previous work, and that was kind of usual for those experiments up to that point. And nothing too great about that. And these things have to be done in the darkness. There were no iPods at the time, I remember. About the only thing to pass the time was playing Minesweeper. So it was a Friday afternoon, it was cold, November, grey day, and suddenly this thing sort of appeared. And I remember it very, very clearly when it first showed. Because here, the electron spectrum, rather than being this broad, ugly thing as before, you see quite a lot of the electrons are, this end means highest energy, all up towards the highest energy part of the spectrum. And we tried this several times. I mean, I ran back and told Chris about these results. You could see Chris still wanted to go home, basically. Everybody else had gone. But anyway, I persuaded him to take a few shots, and we were able to show that over a certain range, we were able to get these kind of reproducible spectra quite a lot of the time. These kind of monoenergetic spectra a lot of the time. And the big thing about that is, what we've shown is not only have we accelerated electrons in that wake field, but we've managed not to destroy it in the process, which was kind of our goal in the first place, right? Anyway, a few months later, we managed to repeat the experiment, got even narrower energy spectra, and this was published in Nature as well. In fact, it was a front cover of Nature. If I turn this on its side, you can see that it looks like the little bubble shapes that I showed you before in the cartoons and whatever. In fact, the editors of Nature, in their wisdom, decided that this was one of their top 10 stories of 2004. And who am I to argue with the editors of Nature, right? And one of the immediate impacts of this work, I think, was that there was suddenly a big impetus to accelerate, if I'm allowed to use that word, the laser development of the Rutherford Lab. So the Rutherford Lab had this plan to upgrade the Astra laser to more than 10 times the energy we had before, which means we could drive our accelerator from even longer distances. Here's another couple of our students who worked on that experiment. And indeed, now we're going from millimeter to centimeter scale. Here's our plasma that we generate through an interferometer. Some of you, again, have seen that in my office. There's an interferometer in my office as well. And we see that as we increase the length of our acceleration, we're now going beyond 100 MeV. We're going to GeV energy scale, which is the kind of tipping point where high-energy physicists start taking interest in these things. And again, it's a GeV almost. In later experiments, we've actually gone beyond GeV. It's a GeV in a centimeter, so that's 100 gigavolts in a meter, which is, again, a Higgs boson in your living room, if you like. But there's another, and so kind of up till now, I've sold almost everything on applications to high-energy physics, which seem still pie in the sky, right? GeV is still a factor of 1,000 away from TeV that Large Hadron Collider is at. But GeV, I mean, there are plenty of accelerators around the world, right? And quite a lot of them have very mundane uses. They're used in medical physics. Quite a lot of, for example, cancer therapy is done with accelerators that produce photon beams that kill tumor cells. And a lot of other scientists use accelerators as well. So this is another accelerator. My brother's been doing an experiment there recently on the diamond light source, which is neighboring to the CLF. I think the CLF is somewhere on this diagram, is it? No? No, sorry. CLF is very small anyway in comparison, so you'd hardly see it. But this thing is a really big application for accelerators. And what this diamond light source is a synchrotron accelerator. As we saw before, right, when electrons move around, when they're made to bend around in orbit, they radiate. And so at certain points in this synchrotron accelerator, the electrons going around in this circle are made to bend even more, and so they give off lots of radiation. They give off anything you want, almost infrared, X-rays even. And you can use them for all sorts of applications. People do that. My brother uses them for crystallography. Other people use them for imaging, for advanced probing experiments, all this kind of thing. There was something I didn't tell you about our accelerator as well, actually. And that is, I showed the electrons slipping back through and being accelerated in a bubble accelerator. Well, one thing that was kind of inaccurate about that is, obviously, if they come in from the side, there's nothing to stop them just carrying forward if they have a transverse velocity at the point that they cross this axis. And so they'll go past the point, past this zero line axis, and they'll have a motion that looks a little bit like this. They just move up and down, they wiggle. The professional term for this motion is called wiggling. So you've just seen an electron wiggling. And what this is a plasma wiggler. And so, again, if I showed you what the electric fields of a wiggling electron are doing, this is what the electric fields of a wiggling electron are doing. And as you see, there's radiation all around, but in particular in the direction in which the electron is moving, what you see is that wiggling radiation is a purely electromagnetic wave. It's radiation of some kind. And in particular, the faster you move this, the faster that wiggle. And so the smaller the wavelength of this radiation. So you can easily, if you get to GeV energy scales, you can easily generate X-rays with it. You generate copious amounts of X-rays. And that's really what a synchrotron, the main source that people use synchrotrons for, is X-rays, which are very highly penetrating radiation, right? And so, actually, when we did our experiments on Gemini, looking at the first GeV-type acceleration, what we could see is once we bent our electrons away, there indeed was this X-ray radiation being beamed along because of the wiggling motion of the electrons. And the amazing thing about this is because of the short time durations that all these things happen, I've been talking about less than millionths of a second, and the very small spatial dimensions that it all happens, the brightness of this beam is incredible. The brightness of this beam already compares with diamond light source. I mean, it has different properties. Diamond light source can be operated very, very fast in very, very many shots and be given to very, very many users. But ours is a really, really compact accelerator that can give almost the same brightness and incredible temporal resolution, for example, as compared to other light sources. And so what can you do with X-rays, right? Well, you can take X-rays with X-rays. People knew that, right? So Stefan, who was our student, whose PhD thesis this was very good at finding dead animals. So he's taken an X-ray of a goldfish here. He's taken an X-ray of a damselfly here. So these experiments were done, I should say, in Michigan here. So it's not a dragonfly. I think maybe there's some difference between damselflies and dragonflies. I don't know. I'm not really an insect expert, by the way. But one thing that's particularly nice about our source, because it comes from a very, very small source size, it has something that's called spatial coherence. Remember, these X-rays are electromagnetic waves, just like any other light. They can interfere, diffract, all this kind of thing. So, okay, you can see that a fly, that's not really very impressive, X-raying a fly, right? You can hardly see any features in that. But if I move my detector away from the thing that I'm X-raying, what you see is suddenly this remarkable resolution in things that you could never think you could see before. In particular, if you think about here, like in the wings, you can see, the veins in the wings, for example. Here, if it was just a question of difference of absorption of X-rays between one part of the wing and the other part of the wing, you wouldn't see any difference at all. The reason you can see these features so very sharply is because there's a very little difference in something we call refractive index. And the X-rays actually deviate a very, very small amount, so that if you take your detector far enough away, you'll see this interference. This is called phase contrast imaging. We think this is an amazing thing. I mean, imagine, right? Everybody's had X-rays, pretty much here. Everybody's had X-rays, and they kind of look like this. Well, we're not flies, I know, but still, they're grainy, and you don't really get to see. You have to be some kind of, you have to do, I don't know how many years of medical school before you can tell people that you have whatever you have, right? A broken bone or a lump in your whatever, Imagine if we could get this kind of micron-sized imaging possible with normal medical X-rays. Well, we think we can do that, and we're actually actively looking into ways of being able to try out these things with human tissue, with biological samples, things like this. We think this is going to be an incredible application for what I told you would seem like a crazy idea 20 years ago, right? But really, the applications are almost there. And, if anybody ever tells you why people do physics, it's very hard sometimes. 20 years ago, it would have been very hard to tell you that this is what we were going to do. We might be able to revolutionize medical imaging, but we think we're at that level of being able to do that. But anyway, that was all very serious. I think I should end with crazy, right? So I motivated this talk on high-energy physics things, and so let's go back to high-energy physics. I told you accelerator physicists tended to hate plasma physicists. That's pretty much the feeling I had for most of my life. Actually, I'm beginning to see a slight change in that. There's thawing in relations, if you would like to say. Accelerator physicists are starting to believe that plasmas could have a significant impact in their futures as well. And so, for example, we've just been made part of an accelerator institute, the John Adams Institute, and we're getting help from accelerator physicists on some of our issues, some of our problems. And one particular example of a project that's related to particle physics is actually trying to go to this energy barrier, right? To be able to get an electron-positron collider at the TeV energy scale. That would be the really exciting thing to be able to do in a collider. And so the problem with, we could still use lasers. I mean, you would have to build a very, very big lasers. The lasers are not yet available for doing that kind of energy range experiment. But I already told you where some of the highest energy density beams available anywhere in the world are, and you know that's at the LHC, right? So if we were to use the LHC beams, which are not the ideal candidate for a particle collider, but they could be the ideal candidate for driving a wake field, and we use the LHC beams to drive a wake field, then there's a possibility we could get to the energy frontier. And so there's only one slight difference between a proton accelerator and a normal laser accelerator. Whereas the laser tends to push everything away, the proton actually protons pull in electrons from the background plasma, and so this is sometimes called a suck-in regime, as opposed to a blowing out regime. Again, not the best names for them. But again, through advances in computation, people have actually been able, I mean, this is an idea that's been going around for some time, but
now people have been able to simulate these kind of interactions, and they've been able to simulate over hundreds of meters, and they actually show that you can get to the kind of energies that they were proposing for ILC. ILC would, at its top level, would be something like a half-tera electron volt in each beam accelerator. And here is a electron beam driven by a proton beam wake field, reaching those kind of energies in just a few hundred meters. Well, again, a few hundred meters, though it's a huge reduction in a typical accelerator, it's a challenge for us now because we don't really do 200-meter long plasmas, not yet anyway. But we've started to try and do that. And so here's a plasma we generated in our labs, and we're working with some of the people I know in the audience here, hopefully trying to make this reality, such to the point that when LHC shuts down for its next shutdown, for its next upgrade to 7 TeV, they're going to let us go into a tunnel and install some of these bits of equipment and see if we can pass a proton beam through them and actually drive some wake fields, which will be quite an amazing thing. It's plasmas actually coming to the LHC, so that will be quite an amazing achievement. Okay, I'm at the end of my talk. Thank you, especially the people at the front, for paying such great attention. I've shown you that we made huge progress in plasma acceleration in the last 20 years. We can generate, with some tricks along the way, we can generate narrow energy spread beams. We started even talking about applications of these beams. We think we could make, in a room almost this size, we could make a little a compact plasma accelerator that could have applications in imaging. And, as I said, we're taking plasmas to the LHC at some point, so that's particularly exciting. One last slide. A lot of people. So I said we were going towards accelerator physics. It almost seems like an accelerator physics talk now, doesn't it? I've had the privilege to work with a lot of people. I'm sorry that I can't name all of you by name, but the amazing thing is that I'm in contact with a very large proportion of the people that I worked on. And also, not everybody's name is here. I just picked out the 100 people I'm most cited with in my papers. That was the easiest way to do this. I'm sorry about that. But there was one particular person that I did want to single out of all of those people, and that was my supervisor, Bucket Angor. He was the guy who told me this crazy idea 20 years ago, though he made it sound very plausible at the time, so that's why I ended up doing a PhD with him. And there's many other things that Bucker started in this group. He was the one who initiated all this work, and he started a lot of things which I didn't have time to talk about today. And so if we're celebrating this work, quite a lot of it's through to Bucker. And of course, he's going to be saying something about me nice in a few minutes' time as well, aren't you? So again, thank you all for your attention. Thank you.